So you mentioned stoichiometry, for example. So stoichiometry basically is going to set the stage for us, for our understanding of combustion. So if we look at it from a very basic equation, you've got one carbon atom combining with one oxygen molecule, giving us one molecule of CO. Okay, which looks very simple. And the more complicated you feel, the more complicated the reaction would be.
Absolutely.
But are there any facets of stoichiometry itself, which you think beyond just the textbook part, or is there something else the average student or the average person from our audience needs to know?
The normal combustion. Forget about the rockets where there is oxygen which actually is in concentrated form, which is carried in them. All other forms of combustion basically use oxygen from atmospheric air.
Yes.
So when we talk about oxygen from atmospheric air, we are speaking about a composition which is 78% nitrogen.
Yes.
So only 20% of the atmospheric air is oxygen, which is actually useful for the combustion that we are speaking about. So the 78% is something that comes as a uninvited guest. It is inert, but it still is important in the fact that it actually is going to be taking away a lot of the heat which is going to be produced as a result of combustion and going to go away. So there is no way we can actually limit it, because we need that 21%, so the 78% comes uninvited.
But it's not
in normal case. Yeah, we can't do anything about it, because as engineers we have to deal with economics.
Yes.
So I can't go ahead in concentrating oxygen and then providing that kind of a concentrated oxygen to any of my furnaces or my boilers or my burners.
Yeah.
So what we get and what is economical for us to do is to basically get atmospheric air and use it in our boilers. So what we were speaking about here is stoichiometrically it is like what you mentioned, C plus O2. I'll put another equation where we say methane, CH4, plus 2 moles of 2 molecules of oxygen, 2O2, will give CO2 and 2H2 water. And of course it's an exothermic reaction, as we all know. So there is a lot of heat which is produced as a result, and there is a lot of heat released. But in practice, this reaction doesn't go this way. You need a lot more air in excess of what is actually required stoichiometrically. Why do you need that? Because if you go as per the stoichiometric air, and if you provide exactly the same mass, the same number of moles, then you have a issue of incomplete combustion. The net result is you will anyway get carbon dioxide, but you will also have a lot of carbon monoxide. So it is something which happens in practice. So it is in practice important that we give air in excess of what is required stoichiometrically. So that is called the excess air. Right. Now this excess air percentage varies between, let's say, 10 or 15% in the case of gas to about 20 to 25% in the case of oil when we talk about fuels. Or it can go right up to 40% when it comes to solid fuel fed boilers. But an excess air is necessary because otherwise we have a problem.
Good. So excess air, my understanding of this is that we need excess air because not every particle or molecule of fuel is going to find an oxygen molecules to pair with during combustion. So it's a mixing problem rather than a stoichiometry problem. That's how I'm.
That is correct. In practice, I'm a chemical engineer. So when it comes to designing of an equipment, so we all have to design something which is economically a viable one. So when you speak about a reaction, and when you speak about pairing two molecules, then it has to happen within a certain residence time.
Yes.
You don't have forever. You don't have unlimited space. You do not have unlimited time. Everything has to happen within a certain time, within a certain space, and it has to happen economically. So that all our designs are based on that. So So it is practically very important that we carry a certain amount of excess air, and we spoke about the fact that any air in excess of what is required for stoichiometrically is not beneficial. It is not going to be participating in combustion in any way.
Mm.
Forget about the nitrogen part of the air. Even the oxygen, which is in excess, is not going to participate. But it is still important, because if that wasn't the case,
Yeah.
then we would still have a lot of carbon monoxide. So modern day processes, modern day engineering works to limiting this excess air
Alright.
to what is absolutely essential to ensure that our combustion process is efficient.
Yeah. So stoichiometrically would be the ideal condition, and how closely we can approximate that ideal condition is where the engineering part of
Practical part of it. And in fact, if you look at the boiler industry per se, the oil and gas fired boilers basically have the burners where which controls the combustion part of it. Now, most of the developments over there have been to control the air to fuel ratio. In fact, if you look at air to fuel ratio control, it is the most important function which basically most of the boiler engineers deal with today.
Right.
So the same is the case even when it comes to solid fuel fired boilers. Although you do not have burners,
Right.
but the combustion over there is very important. Although it takes a different hue,
Yeah.
it takes a different shape, but again, air to fuel ratio is very, very important, and we need to get it right to make the operation not only efficient but also safe.
Yeah. Okay. So yeah, and we discussed this earlier in our discussion also, where the safety is very critically linked to most of the combustion applications. If you want to harness it the way you placed, the way you said earlier, so the harness will always go hand in hand with the safety aspect of it, right?